Good afternoon, everybody. My name is Çağatay Büyükkoç. I am the lead RAN architect within AT&T, and I am one of the three speakers this afternoon. Thank you for joining our session.
Hi, I'm Hasib Akhtar. I'm with Ericsson, and I'm collaborating with my fellow speakers here.
This is Kandan Kadirvel, Director, Cloud Strategy and Architecture from AT&T.
Okay, the talk is going to work related to what 5G architecture is and what are the new 5G capabilities. And so what is 5G? 5G is basically not one more generation of 4G, but it's more like a new set of capabilities that are brought by the industry as a result of the developments in SDN, NFV, and distributed distributed compute architecture or edge computing. So they all come together to bring us this new technology in a very different architectural framework than the previous technologies. So if you look at the 3G, 4G, 5G evolution, there are lots of commonalities in terms of, what you can see is there are certain amount of peak data rate, certain amount of throughput, edge throughput, latency, etc. So if you look at this left-hand side diagram, so probably all of you are very familiar with this. This is basically the extreme points capabilities of what 5G is going to be defined on. So if you go through this throughput, spectral efficiency, mobility in the orders of 500 kilometers per hour, latency in the order of like 1 millisecond, which is extreme low latency, connection density. So these are what is being defined by ITU-T, as you know. So if you come back to here, so you will see that there are certain data rates that goes gradually increases by each generation, and then also related to previous generation of networks, 3G and 4G. So you have a fixed set of boxes with certain capabilities at certain locations. So the most important difference of 5G from the previous generations is that you have a total flexibility of what function is going to go where. So that's actually our story is going to focus on those, as well as like technology advances has brought air latency from 10 milliseconds to 1 millisecond, and QoE from the user experience point of view has tremendously going to be impacted and for the better. So these are the overall capabilities of 5G. Now, as I said, a technology is defined by its extreme points, right? So if you are not at the extreme point of a technology, you are pretty much similar to previous technologies. So we looked at the 7 key KPIs. This is like a very well established across the industry. So what are the key KPIs, key performance indicators that impact a user's experience? So if you look through them, throughput, latency, reliability, mobility, availability, energy efficiency, and the user device density. So we say, okay, so these are our key performance indicators. And then we have a heptagon of 7-dimensional polygon of extreme points of what these technology extreme point is going to be. So as we go, I'm going to show you now like go one more. And as you go to the inner heptagons, it's the KPIs are relaxed. So the extreme points will define 5G as specified on the left-hand side. So what are the use cases that we are going to map, or what are the use cases we are going to use this 5G technology? I mean, everybody's talking very excited about 5G. Is it going to be like extreme low latency or extreme high bandwidth, or do we have lots of use cases with lots of KPIs as specified here? So the industry is focused on 5. These are not use cases, but 5 categories of use cases, right? Categories of use cases are mobile broadband, right? That's a big category because this blue curve shows you the performance hyperplane that provides what mobile broadband can be. So if you look at the extreme points, it can be an extreme available network it might require, or extreme mobility. So you are on a train going 500 kilometers per hour, right? This is a very high mobility case for MBB. But there are also lots of other, you are sitting in your home and you are doing some kind of web application that also falls into this. So this is not like one use case, but bunch of use case the capabilities. So the next one is massive MTC. So this is a new use case that because we have tons of sensors and devices that with very limited capabilities, and what do they require? So we look at all these KPIs. You can do the intellectual thinking of what are the extreme points. You want availability, energy efficiency, because you don't want to change the battery, and then extremely dense, because you want them thousands of devices per square kilometer. If you see the left-hand side, so it shows you like 10 to the power 6, I believe, devices per square kilometer, which is the extreme case of this dense. So this specifies the second one. The third one is basically like information society where you are using lots of learning tools. You are doing some video experience over the web or internet. So you can just trace the KPI for this example. And then you have obviously connected cars. Connected cars is a big use case. You hear about it all the time, and that requires a lot of extreme points of 5G, but as well as some applications that actually some connected car applications do not require these extreme points. So this curve is like that. And the last but not least kind of falls for the virtual reality is probably one of the most talked about new applications that require the extreme points of 5G. So in effect, we have these categories. So what do you do? How do we prioritize? How do you deploy? So our story is going to trace. So we have all these use case categories. We have all these capabilities. And how do we define an end-to-end network? And what are the important so the network architecture in our mind has 4 components. One is the functional architectural view. So what functions do you have at the RAN and the core? And then next one is the deployment view. So since we are saying everything is flexible, where do we put what function to what location? right? And then you have a resource view. So what type of compute network storage requirements do we have? And then the last and probably the most important view is the topology view, because that's the most costly view. I mean, where do you actually physically put those compute storage networking capacities in the actual network? So this is the story of, I'm going to come back later for the architectural vision for end-to-end architecture.
Thanks, Itai. So, I actually, to continue with the story, we're now looking into how do we make this relevant for the edge cloud. So if you look at the use cases, we have the massive, the MTC, the machine type communications, which has low cost, low energy. It has small data volumes, but they're very large in numbers. That's kind of on the one extreme where you need to have closer to the edge. And then on the other side, on the critical MTCs, which are reliable and then requires low latency, and they have to be available all the time. So both of this end of the spectrum actually requires these functions to be placed at the edge. And then in between, you have the enhanced mobile broadband, which is our basic use cases that we're using today, like what Shatai mentioned, that on the extreme side of the edge or extreme side of the polygon that he shared, you have those critical and the massive MTC use cases, and then the enhanced mobile broadband, which is home enterprise, as well as some of the AR/VR use cases that sits in the middle. But the point here is that once we put things into the edge, we have a special requirements as well as the benefits that we get out of it. So we can put content at the edge that will minimize the delay and as well as reduce the cost. We can do a lot of processing in terms of the data science analytics. We can also offload some of the compute, such as session breakout in the 5G terminology. So those are some of the things that could benefit by putting in things at the edge, as well as we have from an user experience perspective, we get immediate low latency based experience on the AR/VR case, for example. Also on some of the remote medical use cases, high bandwidth, as well as the availability and reliability. And Kandan will go more into those from an infrastructure and the resource orchestration perspective and how do they relate to edge. Moving forward, what Shatai mentioned in terms of weaving the story, we wanted to kind of now look into the deployment model. So what I've done here is that kind of segmented the network into different sites or data centers, as you may call it. So we have the devices and the cell sites, and then the access sites, which is very close to the cells. Then we have the local sites, and then regional and the national sites. So those usually are the one how the operators would distribute the network. And then for the massive MTC use case, those are low cost, low energy, and the small bandwidth, but in large numbers. So you'll see them located, mostly at the regional sites, and those would be your control plane with a connectivity with your wireless, backplane going all the way to the cell sites. And then, of course, you will have your lot of the control plane and the user plane in the national site. And I have grayed out the RAN and the core network in two separate boxes so that you can see the placement and the flexibility of the 5G network. And the things that are on the cell site, on the kind of black components, those are, we call them peripherals or physical network functions. Those are still, even in the 5G, are going to be physical network functions. or purpose-built hardware, so to speak. And the ones that you are seeing on cloud infrastructure, those are basically virtualized. It could be VMs, it could be containerized. And then the difference between the yellowish and the kind of red colors are that the red things are part of the 5G components, 5G network components that have been virtualized. And the applications are any applications that would run either at the edge or at anywhere else to utilize 5G or any other access network. So moving forward, the next thing is our enhanced mobile broadband, which is basically the typical mobile services that we use. And if you notice that those would still be at the local, regional, and the national sites with control and the user plane distributed across. And that's typically how it is done today. And one thing that I'm showing there on this use case, that some parts of the cell or the RRU is moved towards the local network. It could go into the enterprise, or it could go into some of the users all the way towards the user side. And then finally, if you go into the critical MTC on the very high availability, reliability, and low latency use cases, that's where you see the things starts to move more towards the access, towards the edge. You see that both core network as well as the RAN virtualized functions have been moved from the regional and the local side towards the access side. So that's where you'll see that the deployment model where you could use the 5G's flexibility to provide and serve these use cases. So finally, to kind of tie the end of the 5G part into the edge. So what I've done is I've taken the edge data center and then took the centralized data center and distributed the RAN and the core network functions. So basically, the key message or the takeaway from here that there are some functions in the RAN will still be purpose-built physical network functions, mainly because of the latency and the delay-sensitive requirements that you have imposed on the access network. And then some of the other part which are on PNFs today will be disaggregated and then distributed across different parts of the network. And in this use case here, what we're showing that the control plane and the user plane of the central unit, which is at the disaggregated part from today's kind of the E node B, if you speak the 5G term, that goes into the edge data center, and then you can run any applications in terms of either a breakout sessions or any other session application running on that edge network. And some of the centralized core network functions could stay in the centralized data center as well. So with that, let Shatai finish up the architecture part.
Okay, thank you. Okay, so let's get back to an end-to-end vision of...
Chatai mic, ikkada switch on.
Okay, let's get back to the 5G architecture story. Now, as Hasib mentioned in passing, like control plane, user plane. So actually, separating control plane from user plane is a very big deal. That was not been possible if we didn't develop this SDN technologies. So, and then putting all these functionalities in containers or different types of workloads that you are very much focused on, it was not be possible with our previous generation networks where we didn't have NFV capabilities fully developed. So in this picture, you see kind of cryptic vision of end-to-end, starting from the RAN, radio access network. So it's a very interesting thing about 5G RAN is not, you don't have one element that defines what a RAN is. So we basically have a distributed architecture. So you can actually have 3 pieces or 4 pieces of where you can place these set of capabilities, very different from the earlier technologies. So this flexibility is bringing great many capabilities that are unheard of. That's why I said 5G is not 4G plus 1, but it's basically a brand new set of technologies. So if you look at this picture, you have the UE, CPE, the basic devices that the users use, or end devices, sensors, etc. And then we have a new element, 5G architecture on the radio consists of 3 elements, RU, DU, and CU. And these 3 elements are mostly going to be virtualized, but sometimes you might actually have a physical network function most of the time because you don't have the capabilities so far. So this is basically a disaggregated RAN. And then we have a similarly disaggregated core. So instead of boxes that have all these functions that will do a given set of functions, here we have a set of functions that we can flexibly put into those 4 or 5 locations. So those are fundamental architectural locations. Centralized clouds, edge clouds, base stations, and macro the radio units, there's antennas, and then so what differentiates these from like topological sense is that there's a control time scale. So if you are interested in control theory, you know that certain actions that you are exerting on the control have to be completed in a certain amount of time, otherwise it doesn't do the impact. So we have, this is an industrial thing that we have looked at different scales of functions, control time scales. 1 millisecond or below are this radio, this because it's ultra fast, there's RU related functions, so which are potentially not virtualizable with current technologies. And then you have DUs and CUs all the way to external contents with different functionalities. Okay, thank you.
Okay, thank you guys. So they talked about what does really 5G means to virtualization and what components it's going to be virtualized and what's going to stay as a physical network. And how does that apply from other use cases? Because when we talk about edge computing, it is not just about the 5G, even though we're talking 5G on this particular topic. There are other workloads from telco and enterprises is going to need to be supported with respect to the edge computing. And here you can see the 4 boxes that represent a different type of workloads that can actually go into the edge computing. So the first one, what we are seeing is like IP enterprise services. These are network functionalities that are actually supported by telco today, and that need to be supported with respect to the virtualization. And some are already virtualized, and some are already been deployed in the cloud world. But with respect to the new latency situation, you do really need a platform like edge computing where you can actually run this closer to the user. Then the second one is what the technology evolution. That's what like Chatai and Hazib actually covered it in a very broad spectrum about what about the 5G is going to do, what is the wireline is going to do. The third piece is actually these are items that are going to run on the edge computing in collaboration with the 5G technology or in collaboration with the edge computing enabling technology. So this is something like augmented reality, virtual reality, drones, and IoT and robotics. And these things actually would require edge computing to be very closer to the user and do the processing, like in a quicker form so that it can actually deliver the output as quickly to meet the requirements of the edge application. So if you look at the last bucket, this is a pretty interesting bucket, right? So if you look at actually the providers, who are the telco providers or network providers, they are the one actually has the real estate, which is actually closer to the user, right? So for example, you take for example, if you take AT&T, we have, real estate, which actually connects the user from a cell phone, wireline, and any type of access. And this particular real estate, that is where, edge computing really has to go, right? So this really brings actually a new ecosystem that doesn't exist before, is that, if a third-party cloud need to be hosted, and it could be hosted actually in the telco buildings, and it actually brings up a new context of, sharing in a common API set across any provider, so that the user comes in actually, access an application, which is actually an FIG or edge computing requiring application. Then pretty much, any telco provider can support it, as long as they actually support a single API interface that actually all providers could support. So pretty much, these are the key areas that actually brings up from an edge computing perspective. But what are the real benefits we really going to get it out of it? So one is the quality of experience, because without edge computing, what is really going to happen is everything has to be processed in the central computing. Then the quality of experience for the users will go away. So if a user want to actually experience an augmented reality, and it's going to be processed in the central cloud, then it's going to have a lag time, and they don't get the performance that they like to see. And the right content edge, this is another interesting idea with respect to it. So if you do not have a right content at the edge, if you don't process actually at the edge, what happens is that all the data has to be, need to be pulled from the central cloud to the edge cloud. So it is really a bargaining, a situation of, what data can be transferred and actually kept in the edge, so that, the backhaul traffic between the cell site and the central cloud is not overloaded, so that, because the content itself is actually in the edge. The other one is a decompose and disaggregate access function. That is what, they covered that in a broader spectrum, because this brings up actually a more, improvement, whatever we have been seeing with the cloud computing. Because in the cloud computing, we talk about, auto scaling, we talk about dynamic provisioning. These were not the thing which is actually supported with the physical network function. Because in the physical network function, you really have to ship a router, or you really have to ship a switch, and you have to provision it. It takes a long time to actually configure it. But in the VM creation or a container creation, you can do it in a few seconds. And that is what this actually brings up. And the better network resiliency, because when we have a lot of edge cloud, instead of having a 10 location of central cloud, then it provides you actually that a broader spectrum of a resource pool that anybody could actually use. So we talked about where is this edge computing is really going to be deployed, right? Because this is an important question to understand. So we talk about it has to be closer to the user. How closer it has to be? It really depends upon the application, right? So right now the industry is actually trying to solve this mostly in the telco offices or central offices of putting this edge computing in. But over a period of time, the edge computing has to be supported in customer premise. There are some situations that even AT&T, we support edge computing in the customer places. And in this case, really the scale goes up when we actually go closer to the user. The reason is that, more we go closer to the user, the number of users are large, and we really have to deploy a many number of them. And then, when you go actually closer to the centralized side, then the number actually goes down. The real key is that from a provider or the person is really going to deploy this, they need to be actually mindful of that, how many locations they're going to deploy. Because when we deploy in the, more locations, like 10,000 or millions of locations, the complexity of managing that cloud actually is really exponential. Because, when we talk about centralized cloud, the whole reason people went with the centralized cloud is that, to reduce the complexity, because I only have 10 locations to manage. But now we're talking about thousands and millions of locations, and it's really a lot of locations to manage. So this brings up additional requirements into the OpenStack that is not something we were talked about before. So if you have attended the Open Dev conference, and there was a lot of discussion about, like what are the use cases. And here is a highlight of things that we should be looking at from an OpenStack community that we need to start addressing it. So the number one is like a community has to recognize that, like EC, the edge computing is an important goal. The reason is that, if we do not solve actually with edge, OpenStack, then there's going to be something else, like it shows up, and that interrupts the, like the community that we already have been built and which is actually working perfect. So what we really needed from the OpenStack is that, we do really need a thinner, lighter OpenStack. And tomorrow I'm going to talk in another session in a more detail, like what does that really mean, right? The thinner, lighter OpenStack, why do we need it? Because, in the large data center, we have a flexibility of deploying the OpenStack probably in 3 server or a 5 server or 10 server configuration, depending upon the number of compute and the scaling. But in the edge computing, we don't have that luxury because the edge itself could be like a single server or a 2 server configuration. And you don't get that much of real estate to actually deploy a full-fledged, OpenStack with a 10 server configuration in the edge because the compute itself is like a 1 or 2 server. So it has to be really thinner and lighter. So there is also a context of, like whether we can do a regional management from the OpenStack. That is also another interesting idea that the community should pursue. The key is actually that it has to be smaller or it has to be in the regional location so that it can actually manage the remote location. The another thing is like zero touch provisioning is a key because when we talk about thousands and millions of locations, there is no way that like we can have a script or a manual person going and actually doing a manual task. That would interrupt the business model of the edge computing. So we do really need to make sure that we provide a zero touch provisioning as an important thing with respect to this. And support massive scale, right? So because people talked about hundreds of data centers and people talked about, across the globe, yes. But the thing is like here we're really talking about not hundreds, we're talking about thousands. We are talking about, millions. So this is entirely a different ball game compared to the centralized cloud. So massive scale is something an important use case. And support modular deployment, this is also another important thing. Why do we really need to support a modular deployment? Because we cannot deploy every aspect of OpenStack into the 2 servers or 1 server where we have to package it up. The reason is that it really has to be like only the component which we really need, that is only need to be deployed in the edge. And support new technology faster because CPU is not the only thing which is going to be used in the edge computing because there's going to be a GPU, there's going to be a FPGA, there's going to be NPU. There's a lot of hardware acceleration technology coming up because especially in the edge, the latency is a key. The latency really comes from 2 things. One is comes from the networking. Then it also comes from the compute processing. If processing takes a long time, then reducing the network latency, putting closer to the user doesn't help a lot. So you really have to have the computing power very high so that the processing can be done very quickly. And support integration with other technology. This is one of the key themes in the community. Jonathan today, he talked about that in the keynote. And it is very important that we integrate with other community because there is not going to be a one solution. It's not just going to be OpenStack powering the edge computing. There's going to be containers, there's going to be a SDN, there's going to be many other technology which you really need to come together to create this, what we call as an end-to-end edge stack. And this can only happen by collaborating with, Linux Foundation, collaborating with other open source technology to bring it up a whole stack, which is what we call as an edge stack. Okay, so we can take few questions. We only have a few more minutes. And okay, so question.
Thank you.
Sure.
Your talk was mostly about 5G and the 5G use cases and how they apply to the edge. But at the end, you also opened up some of the wireline use cases. And I wanted to get your thought. What's the benefit of having a single, or is there a unified solution between the virtualization technology we will use, like OpenStack at the edge, between wireline and wireless? Is there a need to have just one, or are we looking at federation here?
Yeah, so I don't see a difference between, how do we use the centralized cloud versus like edge cloud from technology, multi-tenancy, and having the platform shared between, like a multiple user or application. Because we are not affordable to actually go and build multiple different sort of cloud for a purpose-built cloud for each application. Then it will be very expensive to build and manage and stuff. So reuse of the platform for multiple application is really desired, but there is going to be a little difference between a generic, very enterprise application which can purely run on container versus like applications like a virtual network function, which would actually need SDN technology or a complex configuration. So there is a balance need to be done, but at the end of the day, like having a common platform, it does actually helps from a cost perspective.
My question is in terms of the edge compute. You're dealing with the end user traffic, which is an IP traffic, and normally in a packetized radio, you have tunneling. Mm-hmm. Where do you extract the user traffic, especially when you have an edge compute closer to the stadium or the home? What's the IP route to get that user traffic to the MEC?
Yeah. So that's actually one of the fundamental questions that this 5G architecture is going to be addressing. So as we have shown in the flexible architecture where the UPF, basically this UPF actually represents the data plane functionality that you can terminate at any location, but for the type of applications you mentioned, we are thinking that they will be terminated at the edge cloud, somewhere closer to the end user, so that you do many of these things that you can do with current technology. So the current technology, we have this tromboning effect, right? So whatever has to go either to the core, come back to the end user, is called trombone effect. So instead of that actually has multiple problems. It uses too many resources, network resources. It causes end user QoE degradation. So this is basically one of the new flexibility that you can place these, and then separation of control plane and user plane and placement to wherever you want. You want to add?
If you have further question, we can talk after the talk. Thank you.
Yeah.
Right, thank you. So I continue this diagram questions. So I saw different terminology here. For example, you have edge cloud, also mentioned before about cell side, also mentioned our access cloud. So, so what is the difference between the access and the cell side? I have a second question about what is the difference between the mobile edge computing, which is standardized somewhere.
Okay. So
I can answer that. Yeah. I think the industry is still struggling to come up with the common terminology, right? So edge computing, from mobile edge computing, like pretty much it's solving the same problem of, like having a compute instance which is closer to the user, right? It's a different community using a different terminology, but I think edge computing is actually currently, like mostly commonly used at this moment. So whatever we are referring here actually from edge cloud, edge computing, it's the same thing, having a compute which is actually closer to the user, right? That's what it is.
Can I add one more thing? So one key use case or key architectural element in 4G was what HC MEC was trying to build through this HC MEC middleware closer to the base stations. But when we come to 5G architecture, I think I'm running out of time, so they're telling me that, okay. 5G architecture is the flexibility, gives us the capability that we can put the context information to anywhere we like. So that's why this edge compute becomes like a key architectural element of 5G. So we can talk more. I think they're kicking us out.
Thank you so much.
All right, thank you.
Thank you.
Thank you, guys.
Thank you very much, guys.
Thank you.